All right. Hello, everybody, and welcome to the third lecture of the GPU computing class. So today we continue our discussion from the previous week, and we'll talk about CUDA model and also data parallelism in the continuation of what we have explained so far. So particularly today, I'm going to talk about the compilation, just from a high level point of view, how we compile CUDA code and what happens internally. And then I'm going to talk about multi-dimensional CUDA grids, and then we're going to have some examples and some code snippets that I'm going to show you. All right, so if you remember from the previous session, so basically when you launch a CUDA program, you launch a grid of thread blocks, as you can see here. So here we are launching 4 blocks, and each block has 4 threads in it. And CUDA organizes these grids using some variables that you can have access through your CUDA kernels. For example, the grid dimension .x gives you the number of blocks like along the x direction, and as I mentioned, CUDA supports up to 3-dimensional axes. So you have grid dim .x, .y, and .z. So today we are going to talk about the other 2 dimensions as well. And you can also get the index of each block using this block IDX, again along the x, y, and z axes, and also thread index and block dim, which gives you the number of threads within the block. And you saw that based on these variables, you can identify a global index for your threads, and then you can assign a concrete task to your thread, right? So for example here, we wrote a vector addition kernel, which is a kind of C function, similar to C function, but we annotate it with this global keyword, right? And then within this kernel, we identify the global index of the thread that we want to use for performing some operations. And then we have these boundary checks because we don't want to work on the data that is out of bound. And then we perform our calculations. Just let me. Okay. So this was the calculation. And then we compiled the code, and then we ran it, and then we showed how much performance gain you can get when you run your program on the GPU. Okay, so now let's talk about what the compiler does internally when you call this NVCC followed by your program name. So basically, as I showed you in the previous lecture, you write your CUDA programs in a .cu file or a .CUDA file, and this .cu file can contain like normal C++ code and also CUDA code, right? And then you call NVCC compiler for this CUDA file, and NVCC stands for NVIDIA CUDA compiler, and then NVCC start to separate your code. So it sends the C code, the normal C code within this CUDA code, to a host compiler like GCC, and then like a normal compiler, the C part of the code is compiled to like is compiled to assembly language for the architecture that you have, then it runs on the CPU. So the compilation path for the C part of your CUDA program is kind of normal, like as you had before. But for the CUDA file, it first compiles your CUDA code to something called PTX, which is a virtual ISA that is used to have a device agnostic execution. And then there is a just-in-time compiler that takes this PTX file and then compiles it into device assembly, which in this case can be SAS. And then this device assembly will execute on the GPU. Okay? So this is from 10,000 feet how CUDA compiler really is working internally, but you don't need to worry about the details of it because most of the details are handled by CUDA compiler. So it's going to be okay if you just know how to use this NVCC. But the general flow of the compilation process is what I showed in this slide. Okay. So there are some small details that I also need to talk about before we jump into the multidimensional grids. So the first thing that I want to emphasize here is the keywords that you can use when you define a function in a CUDA program. So you have already seen this global keyword, which is used when you want to define a kernel, and a kernel is a function that is executed on the device, and it is called by the by the host, right? This is the function like vector addition that we have had so far. Okay. There's also another keyword called host, and is used when you want to have your function only on the host, only on the CPU. So when you use the host annotation keyword, your function basically is called from the host and it will be executed on the host. We will see in a minute why we really need that. And host, a keyword, is going to be default when you write any function. So if you don't annotate your function with any keyword by default, when it comes to NVCC compiler, it's considered to be a host, which means it compiles only for the CPU. Okay. And the other keyword that we have is the device keyword for annotation. And this keyword is used when you want to call a function from the GPU and also execute it on the GPU, right? So now the question is why we really need host if by default our function in our C program is executed on the host. So you can think about it for some moments. I guess you can pause the video here and think why we really need the host keyword. All right, so I will show you why we need the host keyword. It basically is needed when you want to compile your program both on the GPU and also on the CPU. So let's take a look at this example that I provided here. So again, we are working with this vector addition kernel, right? And we want to add 2 elements. But now assume we want to also have this vector addition function to be compiled on the CPU. And we need that because, for example, at the moment we don't have access to any GPU. So we want to test our function on the CPU and then we want to have it on the GPU. So that's why we probably want to have both CPU and GPU versions to be compiled for us. All right, so assume the main operation that we want to do here, for example, this addition, is a complicated operation. So what we want to do, we don't want to copy the code in these 2 functions. So what we do is that we want to factor out the code that is common in both functions and have it in another function. Just a simple refactoring here, right? And after that, I will annotate this function called f with both host and device, which means I want to compile this function for both CPU and the GPU, right? And then simply I can call it from the GPU kernel, which is compiled only for the GPU, and also the CPU function. So one of the applications of this host keyword is when you want to refactor your code and have both CPU and GPU versions available. Okay. Another thing that I mentioned previously is asynchronous kernel calls that happens on the GPU. So by default, we know that the kernel calls are asynchronous, which means when your CPU calls a kernel on the GPU, so the CPU basically does not wait for the GPU to finish the execution, right? So in case you want to wait until the GPU execution or the kernel execution on the GPU finishes, you have to call this function from the CUDA API called the CUDA device synchronous. So in this case, the CPU execution will block until the execution on the GPU completes. All right. The next thing is how to check errors. So I also mentioned this previously, but it's quite simple and similar to how you check errors in C. So for any CUDA like function call, you get an error like type called CUDA error underline T, and then based on this error type, you can see what kind of error, for example, like memory allocation error, CUDA device error, device synchronize error, and so on. You can get kind of information what kind of error is that you're getting and what's the problem here. There's also another type of API call for getting error, which is called CUDA get last error, which gives you the error that could happen within your kernel. So these are basically two different ways for getting information about the error in your CUDA program. Okay. So that was some like details that I wanted to cover, like the compilation, asynchronous calls, and different keywords that you have, and also how to handle errors. And now we are going to talk about the multi-dimensional CUDA grids and why we need them and how we can use them. All right, so let's continue. So in order to explain the two-dimensional grid provided by CUDA or multi-dimensional grid, I provide like different examples, and using these examples, I will show you how these multi-dimensional CUDA grids actually work. So the first example is RGB to grayscale, where you want to convert a colored image into a grayscale image. So you can pause the video here and think how you would parallelize this task. Well, the parallelization is quite simple. What we can do is to assign one thread to convert each pixel in the image. So you have like different pixels in the image, you assign one thread to each pixel, and then that thread would be responsible for converting the colored pixel into a grayscale pixel. So quite simple and independent tasks that we have to do on our GPU. So as I mentioned, CUDA supports up to 3-dimensional grids, and that's mainly because since, for example, our data is in 2D, so we want to have our grid also in 2D. So we want to have a direct mapping between our data, the dimension of our data, and also our threads. Otherwise, we have to convert one-dimensional thread indexing system into 2 or 3-dimensional thread indexing system. So that's not something that we really want, and CUDA provides this multi-dimensional thread organization for us. All right, so for example, assume this is our image, and for this image, we can simply define this 2-dimensional grid where we assigned one thread per pixel, right? So as you can see clearly in the right diagram, we have organized our blocks into a 2 by 2 grid, right? So we have 4 blocks in total, and we organize them in 2 by 2 grid, and then each block also is organized into a 4 by 4 like threads, right? So in total for each block we have 16 threads, and these 16 threads are organized into a 4 by 4 thread block. So quite simple idea. So let's see how we can launch such a grid in 2 dimensions. For launching such a grid, similar to what we had in the previous 1-dimensional case, we have to define the number of threads per block and also the number of blocks. So because now we are working with more than 1 dimension, so CUDA provides a built-in type called dim3, where we can use it to define our multi-dimensional block and also multi-dimensional grid. So simply, you can define it like this. So just let me bring the pen. So the number of threads per block is like in the type of dim3, and then you can specify the number of threads that you want to have in your block in each dimension. So you here, for example, I define 32 threads in the x dimension, in the x along the x dimension, and 32 threads along the y direction. And if you don't specify the number of threads along the z direction, by default it considers to be only 1. Okay. So similarly, we can define the number of blocks using the ceiling formula, but here we just use the 2 dimension, right? So the ceiling along the x dimension and also along the y dimension. By the way, this 32 is arbitrarily selected here, but in practice, the number of threads per block should not be more than 1024, because NVIDIA does not allow you to have 1024 more than 1024 threads per block, and we see the reason in the next lecture. But for now, just what you need to know is to be able to use this dim3 type to kind of configure your 2-dimensional grid. And then simply like what we had before, we just can configure the kernel here by the number of blocks and the number of threads per block, and then we can launch the kernel. Okay, so this is how you define a 2-dimensional like threads per block and also 2-dimensional grids using these dim3 types. Okay. So in the 1-dimensional case, we had this indexing system that I also explained today. And we have a similar indexing system, but in the 2-dimensional or at most 3-dimensional case when it comes to multi-dimensional grids. So for example, consider this grid, which is a 2-dimensional grid. So in this case, we have this grid dim.x, which is the number of blocks along the x-axis. And also we have this grid dim.y, which is the number of blocks along the y-axis, right? So we just have 2 dimensions in this case. And similarly, we have block index.y, which is the index of the block along the y-axis, and also block index.x, again, which is the index of the block along the x-axis. And again, we have the block dimension in y and x direction, and we have the thread index along the x and along the x and y axis within the block. So if you remember, previously we had a global index for each thread, and now we have 2 global indices. One of them is the global row, if you move toward the y-axis, and the other one is the global column, which gets you the global index of the thread, like along the x-axis. So quite similar to what we had before, just in 2 dimensions. Okay, now let's see how we can write the RGB to gray kernel, like here. So similar to what we had before, we have this global keyword to specify that this is a kernel that is going to be executed on the GPU. And this kernel receives different arguments. So the red channel, which we use unsigned character because it's color and its value is between 0 to 255, and the green channel, and also the blue channel, right? And these are 2-dimensional arrays that are flattened into 1-dimensional array. I will explain how we do that just in the next slide. So these are our inputs, the red channel, the green channel, and also the blue channel. And then we define a gray array to store the grayscale image. And then we provide the width of the image and the height of the image. Okay? So the first step that we need to take is to compute the global row index and the column index of our thread to identify each thread in the 2-dimensional grid that should work with the colored to grayscale conversion. So the column index is similar to what we had before, right? We just need to consider the global index along the x direction. And for the row, we just need to consider the global index of the thread along the y direction. So nothing complicated here. All right, so but before completing this kernel, let's see how we store 2-dimensional arrays in C for dynamic allocations. So assume we have a 2-dimensional array. Here can be like the color of the image, or like the channel actually. So by default, C uses a row major order to store this 2-dimensional array. So simply it stores it in a 1-dimensional array, and for storing the actual data, it first stores the first row, the second row, the third, and the last row, right? So basically, C flattens the 2-dimensional array into a 1-dimensional array. Okay, if you use this double bracket notation in C, where you specify the exact number of rows and columns here, so the compiler automatically does it for you. But if you want to allocate some memory for a 2-dimensional case, you have to do it manually. I will show it in our code like later in this lecture. Okay, but this kind of row major order allows you to allocate 2-dimensional arrays in C dynamically, right? And then you can store them as a 1D array. Okay. And for accessing these elements, you can simply work with the indices. So for example, if you want to have access to like element with row index row and column index col, so you just need to compute it simply by multiplying the row index times the width, and then you have to sum it with the column index, which is the offset. Then you can get the index, and then using this index, you can get the value. So it should be familiar from computer architecture courses. All right. So now let's focus on our kernel. So now we know that these channels are 2-dimensional channels, like two-dimensional arrays, but we stored them in one-dimensional arrays. That's why we have this indexing system here, right? We identified the global row index and the column index of our threads, and then here we just need to calculate the gray value of the colored pixel. So for example, one formula can be what you can see here. So we just consider like 30% of the red channel, 60% of the green channel, and also 10% of the blue channel. We sum them together, and then we store the result into the gray array, right? Which is also a 2D array. Okay, so similarly, the number of threads per block might not fit the number of like pixels in the image. So what we need to do is to have this boundary condition. So we just need to define or use this if statement, and the global row and the global column should be smaller than the height and width respectively. So this if condition is provided only to make sure that we are within the image and we are working with valid data. Okay, so this would be the gray to the RGB to gray kernel that we can write, right? So later in the lecture, I will show you the actual code, and I execute the code and show you how it works in practice. All right, so let's continue with the next example, which is the image blurring example. So basically in this example, we have a image stored in two-dimensional array, and then we want to blur this image. There are many ways to blur an image, but one simple way is to for each output pixel in the output image, we compute the average of the corresponding input pixel and some pixels around that pixel, right? So for example, this here in the right, we have the output blur image, and here in the left, we have the input image. And each pixel in the output blurred image is the average of the corresponding pixel in the input image, right? With the average of that pixel and some pixels surrounded. So, and this can be tuned by some variables in your code, but basically this is the strategy that we follow for this image blurring example. Okay. So now pause the video a bit and think on how you would parallelize this problem and this task into different threads. Okay. So the strategy would be kind of similar to what we had in the previous example. So we can assign one thread to each output pixel, right? And that thread in the output pixel would be responsible for computing the average of the corresponding pixel in the input image and the pixels around that image. So basically each thread needs to read multiple input pixels from the input image and then computes the average and then writes it into the output array. So quite simple approach, but here we have multiple reads from the input image. So let's see how we can write this kernel here. Okay, so here's the kernel that I provided here. So just let me select my pen here. So again, we define this global keyword to specify that this is a kernel and it is going to be executed on the GPU. So we can call it a blur kernel, and then it receives the input image, right? And also it can also receive an array, a 2D array, but in this case, this is a 1D array, but the flattened version of the 2D array for the blurred image, right? And these images, they have R and G and B, but it's stored in 1D image. So everything is flattened, right? And then we provide the width and the height here. So similar to what we saw before, we need to compute the global row index and the column index. And here, because we are working with the output image, so our threads are working with the, basically we assigned one thread for each pixel in the output image. So we just named it as out row and out column, but they're basically the same thing, right? And then we define this, we use this boundary condition to be in the image. So this is also similar to what we had before. And here is the logic for this kernel, right? So we define a global variable called the blur size, which basically tells how many pixels like around the current pixel you want to consider for the average. And then we start with the in row and in column, which basically is the output pixel and minus this blur size. So because we want to have the corresponding pixel in the input image, right? And then we just like have this for loop here. What we do here is to compute the sum. So here we take the sum of the all surrounding pixels, and then when we want to store that sum into the blurred image, we just need to take the average. And here this statement shows the number of pixels that we use for the average. So quite simple logic for this problem, right? So we compute the average. So each thread basically gets the data from the input image, like, and then it computes the sum, and then it computes the average, and then it writes the results into the blurred image. But be aware that here this image array is also storing the colors and the values. So basically you have some kind of storage like this. So R, G, B for the first pixel, for the second pixel, and so on. So everything is flattened here. Okay, so this is the blur kernel, but still we need to check something. So apart from the boundary condition that I told you, we also need another kind of boundary condition for this particular example. So for example, if you are processing this pixel, right, when it comes to the input image, you want to take the average of the surrounding pixels, which also contains the pixels that I'm drawing here. But these pixels are not available, right? So these pixels are outside of our image and they're invalid. The same thing can happen when you are here and when you are here, right? So then we also need another kind of boundary condition, which we can provide it here. So we want to make sure that this in row and in col are within the range. So they should be positive, and they should be smaller than the height if for the in row, and also smaller than the width for the in col. Okay. So as a rule of thumb, for every memory access must have a corresponding guard that compares its index to the array dimension. So basically, like every time that you want to access data in the memory, you have to make sure that your thread is having access to the corresponding like data that is actually valid and available within your data dimensions. Okay. And this was about the image blurring example. So the last example that I'm going to cover like very briefly today, but we're going to we're gonna like talk about it in depth, like in the next lectures, is the matrix multiplication, which is one of the most important operations when it comes to deep learning and AI. So let's see how we can do it using CUDA, but this is a very naive version of matrix multiplication. So from linear algebra theory, we know that like if we want to compute A times B, where A and B are matrices. So when we want to compute A times B, for each value in C, which is the output matrix, for each element of C, we have to compute the dot product of the corresponding row of the first matrix and the corresponding column of the second matrix, right? So the dot product of this row and this column produces this value. So this is simple matrix multiplication rule that we have from linear algebra. So the parallelization approach is also going to be simple in this case. But as I mentioned, this is a simplified case. So again, for each element in the output matrix, C, we can assign a thread that computes that particular element, like here, right? So we can assign a thread to load this row from matrix A, and also load this column from matrix B, performs the dot product, and then stores the result into C, right? In, I think, 2 lectures later, you're gonna see that why this is gonna be inefficient and how we are going to make it more efficient. But for now, just consider this simple strategy that each thread loads the corresponding row and column and then performs the dot product. Okay. So this is how we can write this kernel called kernel. We get the input data A, input data B, and also C. Again, these are 2-dimensional but flattened like arrays. And then we provide the number of elements in the array. So again, we have to compute the global row and the global column for the output matrix, similar to what we had before here. And then we perform the dot product here, which is basically the sum of AI and BI, right? So here we just need to, here we fetch the row of A and the column of B. And then we just multiply them together and then we add it to the sum. And finally, we have to write the sum back into the output matrix. So this is how you write this kernel, but again, you have to check the boundary conditions. So the same thing as before can happen here. So the number of threads per block might not fit the number of elements in the output and also input matrices. So what we do is to check the boundary conditions, but I didn't provide it here, but it's going to be quite similar to what we had before. All right. So now with these 3 examples, you know how you can set up a multi-dimensional grid in CUDA and how you can perform 2D operations when your data is 2-dimensional, like in matrices or images or that kind of data. So in the last segment of these this lecture, I will show you how you can implement the full thing, implement it like in a full code, how you can run this image blurring and gray and RGB to gray examples in C. So see you in the next segment.
All right, so I have shared my VS Code window. So this is my code base. So I have a source file called c2g.cu, which implements both color to grayscale kernel, as you can see here, and the blur kernel, as you can see here. But before that, let's review the CMake file. So here, some standard lines, the version of CMake, the version of C++, the languages, things like that. And first, I need to use this find package to find the CUDA toolkit. But you have to make sure that CUDA is installed on your system because I'm going to work with images. So I also work with this find package OpenCV. So make sure that you have OpenCV also installed on your machine. Then I add executable for this C2G .cu file, and I just name it C2G. And finally, you have to link CUDA runtime library and the OpenCV library to this C2G executable. All right, and by the way, this is my image that I'm going to work with it. So let's see how we can write this color to grayscale and also blur kernels. Okay, so these are the header files first that I need to include. So these two are standard, but I need to include these header files for working with OpenCV. And then I include this CUDA runtime to work with CUDA and CUDA internal variables. All right. So the first kernel is this color to grayscale kernel. So in this case, we have an input image, right? And an output image, both in pointer of characters, right? Unsigned characters. And the image width and the image height. So these are my inputs to my kernel. Then I need to find the column index and the row index of like my threads within this block. Then I check my boundary conditions. And here I do a slightly different than what I showed in the slides. So here the input image is a colored image, and which is like its size is width times height times 3 because it has two channels, R, G, and B. So because of that, I need to find the index of the pixel, but also considering the channel, the channel RGB. So that's why I multiplied by 3. So this is the index of the output of the input image that I want to work with, right? So then I find the R value using the input in this IDX. Then input of IDX plus 1 would be the green channel, and finally I have the blue channel, right? So now I have the value of R, G, and B. Then I just need to convert the color image in the colored pixel into the grayscale pixel. So I can do it using this equation from image processing. And then this is going to be my output pixel, right? So here, because the output image is a grayscale image, so you don't have these channels. So that's why I just use this y times width plus x, right? Row times the number of columns add with this column index. All right. So this is the implementation of the grayscale one. And now I'm showing you the implementation of the blur kernel. So again, I need to obtain the index of the column and the row index of the thread within this block. Then I check the boundary condition here, right? Then I need to identify the index of the pixel in the input image, which is a colored image. So I define a variable for the count, so the number of pixels that I'm computing. Uh, and then I have three variables for summing over R, the red channel, the green channel, and the blue channel, right? So it's slightly different than what you saw in the slides, okay? Then this 5 is my blur size. So I start from 5 pixels before my actual pixel and then continue to 5 pixel after my actual pixel in both rows and columns direction. Then for each for each iteration in this nested loop, I need to find the actual index of the surrounding pixel, right? So X and Y are the center, which is the actual pixel that like the center of this the square that we are working with, and this using this dx and dy, we check the surrounding pixels. All right. Okay. Then we have the other boundary condition to make sure that our squares are within the image, right? Then because the output image also is a colored image, so we also need to identify its pixel by considering the channels, right? And then we sum over the R channel, the G channel, and the B channel, RGB, right? And then we count the number of pixels that we average, that we sum. So after that, we need to compute the output image, right? The pixels of the output image. So we take the average over the R channel and then put it into the output matrix. Then we compute the average for the green channel and the blue channel, and then we write it into the output image, right? So a slightly different implementation, but I think it's more readable compared to what I showed you before. All right. Okay, so now let's see the main function, how we can load the image and how we can like get this image values and so on. So the first thing that I do is to find the image using OpenCV. So this is my image file, image.png. So I just need to specify its address to OpenCV. Then I can use this imread function in OpenCV and specify that this is a colored image, right? To read the image from my disk into the memory, and OpenCV basically stores this image into a data structure called mat, which is a matrix. And then I check if the image is empty. So if it was empty, then I send an error. Then I just like print two lines. So the first one is like image loaded successfully, and here in the second line, I just print to the screen the number of rows and the number of columns. So basically the image size. Then I introduce two variables, width and height. Width is the number of columns, height is the number of rows. And then I have to specify the image size for the colored one, which is width times height times 3 and times the number of like the size of the character, right? Because I need to have the size in bytes. And then I do the same thing for the grayscale image. So in that case, we don't have this 3 because we don't have 3 channels. So it's going to be 1. And then I have to allocate some memory on my GPU. So I introduce two pointers for the input image and for the output image, right? And then I use this CUDA malloc for allocating memories on the device. So first I just allocated some memory for the input image, for the colored image, and then for the grayscale image, right? So after allocating memory on CUDA, we just need to copy the data from the main memory or the host memory to the device memory. So here I pass in the device address, the device memory address, and then here is the data of my image, which is an array, and the size of the data and the type of transfer, which is CUDA memcpy host to device in this case. All right. So now I'm ready to launch my first kernel. So I define the block size to be 16 by 16 threads. And then I define my grid size using this dim3 type in CUDA runtime. And then I launch my kernel. The first kernel is color to grayscale kernel that I launch, right? Then I use this CUDA device synchronization to make sure that my code synchronizes here and nothing happens on my host unless the GPU part is finished, right? And then I need to allocate some memory using OpenCV for storing the output image on my host memory, right? Then after this kernel is done, I have now the output to be filled with data. So I just need to send the result to to the host memory using this CUDA memcpy by device to host, right? And then I just store the image in a PNG file. So this is my matrix that stores the image. And here, using OpenCV, I am writing the image into my disk in the PNG format. So this is about the first image, the first kernel. And now I can also call the blurring kernel. So what I need to do is to allocate some output memory for the blurred image, right? Because in the grayscale case, I had a two-dimensional array, but in this case, I also need to consider that the image is colored. So again, I have to allocate some memory on the device. So I use the size of the colored image that I defined here for the colored image. So this number is not different. Okay, where was I? Okay. Then I can launch the blur kernel using the same number of blocks and the same number of threads per blocks. And then I use this CUDA device synchronize again. Then I allocate some memory using OpenCV for the output image for the blurred one here. And then I write the output, the results to the memory in OpenCV that I allocated using this CUDA memcpy device to host. Then I write the output image uh, on my disk, and finally I just need to free up the memory that I allocated on my device. And by the way, the memories that are allocated by OpenCV are going to be deallocated automatically by the library. So you don't need to do anything about those. Okay, so now let's compile the code. Sorry. Okay. So I just need to create a build folder, and then I navigate into my build folder. Then I compile using CMake. So first I need to configure CMake to find my compilers. And then I can use make to compile the actual code. So let's wait until it's compiled. Then I should have an executable called C2G here, as you can see it here. All right, so let's now run it. I navigate out of the build folder and then write C to G. Okay, outside. So this should be built and then C to G. Okay. So after executing this program, now we have two images in this folder. The first one is blurred image, and the second one is the gray image, right? So this is my original image. So it's the colored image, right? So if I open this grayscale one, so you have the grayscale version of that image, which I did using CUDA on my GPU, and this is the blurred version of the colored image, right? So you can compare it easily. So this is the original image, and this is the blurred image. And everything here was done in parallel using CUDA on my GPU. All right. So this is what I wanted to cover also for today. And thank you for watching this video and have a good day.